Space is often imagined as a great stillness, a silent distance spread between stars, planets, nebula, and the pale dust of forgotten systems. From Earth, the night sky appears calm because distance softens everything. Catastrophe becomes light, collision becomes a point. A dying star becomes a shimmer so small that it can disappear behind a cloud or the glow of a city. The universe hides its violence with scale, and because of that, the human eye receives destruction as beauty. Yet the cosmos is built through upheaval. Stars are born inside collapsing clouds of gas. Planets form inside disks of debris where dust, rock, and ice strike one another for millions of years. Heavy elements are forged in stellar furnaces, scattered by explosions and gathered again into worlds. Even the atoms in blood, bone, oceans, and stone carry the memory of violent events that happened long before the solar system existed. Creation in space rarely arrives gently. It arrives through pressure, heat, gravity, radiation, collapse, and impact. The most violent events in space are difficult to imagine because they exceed the ordinary language of danger. A hurricane, an earthquake, a volcanic eruption, even a nuclear blast belongs to a human scale. In the wider universe, entire stars can be shredded, magnetic fields can crack the crust of dead suns, black holes can feed on worlds of plasma, and beams of gamma radiation can cross billions of light years with enough force to be noticed by instruments orbiting Earth. To understand cosmic violence, we must enter places where matter reaches its final limits, where gravity becomes an executioner, and where light itself is born from ruin. A massive star spends most of its life in balance. Gravity pulls inward, trying to crush the star under its own weight, while nuclear fusion pushes outward from the core, turning lighter elements into heavier ones and releasing the energy that keeps the star alive. For millions of years, this balance can seem almost eternal. Hydrogen burns into helium. Helium gives way to carbon and oxygen. In the largest stars, the sequence continues through neon, magnesium, silicon, and finally iron. Each stage is shorter than the last. The star ages faster as it grows more complex, moving from a long youth of hydrogen burning into a furious final sequence where whole eras of fusion can pass in cosmic instants. Iron is the boundary. Fusion can no longer give the star the energy it needs to resist gravity. The core, once a furnace, becomes a weight. In less than a second, it collapses. Atomic nuclei are crushed together, electrons and protons merge into neutrons. Matter falls inward at enormous speed, then rebounds as the core stiffens into one of the densest objects in the universe. A shock wave forms inside the star and tries to escape through layers of gas that once made up the star's body. Neutrinos pour outward in almost unimaginable numbers, carrying away much of the gravitational energy of the collapse. The star tears itself apart. From a distance, a supernova can outshine an entire galaxy for a brief time. What had been a single star becomes a growing shell of heated gas, heavy elements, radiation, and dust. The outer layers expand into space at thousands of kilometers per second, enriching the surrounding medium with oxygen, silicon, calcium, iron, and other elements that future planets may need. The violence is therefore also a form of inheritance. Without ancient supernovae, there would be far less of the material required for rocky planets, oceans, atmospheres, and living chemistry. The death of one massive star can become part of the deep foundation of countless later worlds. There are different kinds of supernova, and each carries its own signature of destruction. Some mark the collapse of massive stars. Others occur when a white dwarf gathers too much material from a companion star and ignites in a runaway thermonuclear explosion. These Type 1a supernova are so consistent in brightness that astronomers use them as cosmic distance markers, measuring the expansion of the universe through their light. Behind that usefulness lies a brutal event. A dead stellar remnant, compact and quiet, suddenly consuming itself in nuclear fire. In space, even the remnants of stars can become bombs. The aftermath can be stranger than the explosion itself. If the core survives as a neutron star, the dead star becomes a sphere only about the size of a city, yet more massive than the Sun. If the core is heavy enough, collapse continues into a black hole, a region where gravity closes around matter so tightly that no ordinary signal can escape. The supernova is therefore a threshold event. It is the last visible convulsion of a star and the first announcement of something more extreme. In its expanding debris, astronomers read the history of stellar death, the chemistry of galaxies, and the violent path by which the universe became fertile. Some stars die with a violence beyond the ordinary supernova. They are extremely massive, rapidly rotating, and stripped by winds or interactions with companion stars until their cores approach catastrophic collapse. When such a star reaches the end of its life, the explosion can be far more energetic than a typical stellar death. Astronomers often speak of hypernovae in connection with the most powerful long gamma-ray bursts, because the collapse of a massive stellar core can produce narrow jets that pierce through the dying star and escape into space. The star's outer layers explode, while deep inside, a black hole may be forming. This kind of death is highly directional. The explosion may look like a vast sphere in simplified imagery, yet some of the most important energy escapes through jets aligned with the rotation axis of the collapsing core. If one of those jets points toward Earth, distant detectors may register a gamma-ray burst, a flash of the highest energy light known to astronomy. For the star itself, the event is absolute. Its core collapses, its layers are torn open, and its interior chemistry is thrown into interstellar space. For an observer across the universe, it can appear as a sudden wound in the dark, brilliant for seconds, then fading into afterglow. The mechanics are extreme because rotation, magnetic fields, accretion, and collapse all work together. Material falls toward the newborn black hole or compact remnant. Some of it may form a disk, heated to tremendous temperatures. Magnetic fields can become twisted and amplified until they help drive matter outward along the poles. In that moment, gravity feeds the engine while magnetism shapes the escape. The violence is organized rather than random. A dying star becomes a cosmic accelerator, focusing a fraction of its collapse into beams that can travel across billions of light years. For a planet close to such an event, survival would be unlikely. The blast wave, radiation, and high-energy particles would devastate nearby environments. Even at interstellar distances, a gamma-ray burst pointed directly at a living world could damage atmospheres and trigger chemical changes with severe consequences. Earth has no confirmed history of such a direct strike, although scientists have studied whether ancient extinction events might carry traces of nearby astrophysical radiation. The idea remains unsettling because gamma-ray bursts do not need to arrive as fire in the sky. Their danger can be invisible, entering the upper atmosphere as radiation and chemistry. Hypernovae reveal a universe where death can become a beam. They also remind us that violence in space is shaped by geometry. A burst pointed elsewhere may pass unnoticed by a vulnerable planet. A burst aligned with a detector becomes a historic event in human astronomy. The difference between obscurity and apocalypse can be an angle. Across cosmic distance, the universe does not need intention to become lethal. It only needs collapse, rotation, and a narrow line of sight. Gamma-ray bursts are among the most powerful explosions known. They were discovered by accident during the Cold War, when satellites built to monitor nuclear tests detected brief flashes of gamma radiation that did not come from Earth. Later observations showed that these bursts were arriving from deep space, scattered across the sky, and often originating at enormous distances. That realization changed their meaning. A small flash in a detector could represent an event so bright that its light had crossed a large fraction of the observable universe before reaching us. There are broad families of gamma-ray bursts. Long bursts, usually lasting more than 2 seconds, are associated with the collapse of massive stars and the birth of black holes. Short bursts, often lasting less than 2 seconds, are linked to mergers involving neutron stars and sometimes black holes. The durations sound modest, almost trivial, until one remembers the energy involved. In a few seconds, a gamma-ray burst can release more energy than the sun will emit over its entire lifetime, although much of that energy is concentrated into narrow jets. Its apparent brightness depends strongly on whether the beam is directed toward us. The first flash is only the beginning. After the gamma rays fade, an afterglow may appear in X-rays, visible light, infrared, and radio wavelengths. This afterglow is produced as the jet slams into surrounding material, driving shocks that accelerate particles and produce radiation across the electromagnetic spectrum. Astronomers use these afterglows to locate host galaxies, estimate distances, and understand the environment where the burst occurred. A gamma-ray burst is therefore both an explosion and a message. It arrives in layers, first as a violent signal, then as a fading record of motion, density, and cosmic history. The burst, known as GRB 221009A, became famous because it was extraordinarily bright, so intense that it saturated instruments and forced astronomers to reconstruct parts of its signal. It was nicknamed the brightest of all time because such an event is expected to be exceedingly rare from Earth's point of view. Its light traveled for billions of years before reaching detectors in 2022, meaning that the event itself belonged to a much earlier age of the universe. Cosmic violence does not arrive when it happens. It arrives when distance allows it to arrive. We witness ancient catastrophes as fresh alarms. Gamma-ray bursts also show the limits of human scale. A burst can last less time than a drawn breath, yet involve the collapse of a star, the formation of a black hole, or the collision of dead stellar cores. It can be over before a person could turn toward the sky, although no human eye would see the gamma rays directly. Its afterglow may then linger, giving telescopes the time to gather evidence from an event that first appeared almost too brief to belong to astrophysics. In that contrast between duration and magnitude, gamma-ray bursts occupy a strange place in the imagination, the universe becoming violently articulate for only a few seconds. A neutron star is what remains when a massive star collapses and leaves behind a core made mostly of neutrons. It can contain more mass than the sun compressed into a sphere roughly the size of a city. A teaspoon of neutron star matter would weigh billions of tons under Earth-like comparisons, although such matter cannot simply exist outside the conditions that hold it together. These objects spin rapidly, carry intense magnetic fields, and curve space-time around them with extraordinary force. Alone, a neutron star is already an extreme object. In a binary system, two neutron stars can become a slow disaster waiting for gravity to finish its work. As two neutron stars orbit each other, they lose energy through gravitational waves, ripples in space-time predicted by general relativity. Their orbit tightens over millions or billions of years. The pair moves faster, the waves grow stronger, and the final seconds become a spiral of increasing frequency. When they merge, the collision produces gravitational waves, high-energy radiation, and an expanding cloud of neutron-rich debris. In 2017, astronomers detected both gravitational waves and light from such a merger, opening a new era in which the same event could be observed through space-time itself and through the electromagnetic signals that followed. The visible and infrared glow from a neutron star merger is called a kilonova. It is powered by the radioactive decay of heavy elements formed through rapid neutron capture, a process that can build gold, platinum, and other heavy nuclei. This gives neutron star collisions a strange intimacy, the same kind of event that shakes space-time and launches material at immense speeds may also help explain the origin of precious metals found on planets. The jewelry of civilization and the instruments of astronomy can both point back to the same violent ancestry, where dead stars collided and scattered rare matter into the galaxy. The merger itself is governed by physics at the edge of knowledge. Scientists still study what happens to the remnant. It may briefly form a hypermassive neutron star before collapsing into a black hole, or it may become a more stable neutron star depending on the masses involved and the behavior of matter at nuclear density. The equation of state of neutron star matter remains one of the great questions in astrophysics. These collisions are therefore laboratories without walls. They test gravity, nuclear physics, high-energy radiation, and the origin of elements under conditions that cannot be recreated on Earth. There is also a terrifying elegance to the final approach. Two objects, each born from stellar death, circle one another in darkness until their orbit becomes a siren in space-time. The merger happens quickly, yet its preparation may last longer than human civilization, longer than complex life, longer than the age of many stars. Cosmic violence often works this way. It stores energy patiently, then releases it with almost unbearable suddenness. A neutron star collision is a long silence ending in a fraction of a second. Among neutron stars, magnetars are the most magnetically extreme. Their magnetic fields are the strongest known in the universe, strong enough to distort atoms and dominate the behavior of matter near their surfaces. A magnetar can be only a few dozen kilometers wide, yet it contains more mass than the Sun and holds magnetic energy on a scale that ordinary intuition cannot follow. Its crust, made of exotic, dense matter, is locked under immense stress. Over time, the magnetic field can shift, twist, and strain the star until something gives way. When a magnetar releases that stress, the result can be a giant flare. The crust may crack in a starquake, or the magnetic field may suddenly reconfigure. A pulse of X-rays and gamma rays erupts into space, sometimes followed by ejected particles moving close to the speed of light. A magnetar flare can release in a fraction of a second as much energy as the Sun emits over very long spans of time. From across a galaxy, it can still overwhelm detectors. In December 2004, a giant flare from the magnetar SGR 1806-20 briefly affected Earth's upper atmosphere despite originating tens of thousands of light-years away. The event is violent in a different way from a supernova. The star does not need to destroy itself completely. It can remain there afterward, compact and dangerous, like a bell that has been struck with impossible force. The flare is a convulsion of the magnetic field, a release of tension from a dead star still carrying more energy in its invisible structure than entire worlds could endure. In cosmic terms, this is violence through stress rather than impact, a catastrophe born from the internal architecture of a remnant. Magnetars also blur the boundary between small and immense. They are tiny by stellar standards, much smaller than Earth, smaller than many cities in width. Yet their influence can travel across interstellar distances as high-energy radiation. Their size makes them feel almost concentrated, as though nature has compressed a catastrophe into a sphere. That concentration is part of their terror. A normal star spreads its power across a vast body. A magnetar stores unimaginable force in a dead core, where gravity, density, rotation, and magnetic fields have been tightened into a single object. For astronomers, magnetar flares matter because they can masquerade as other cosmic explosions when seen from far away. Some short gamma-ray signals may turn out to be magnetar giant flares in nearby galaxies rather than distant mergers. This complicates the violent universe and makes it more interesting. The sky does not label its explosions for us. A flash of gamma rays may come from colliding neutron stars, a collapsing giant, or the magnetic agony of a stellar corpse. Every signal asks to be decoded, and every answer reveals another way the universe can break. A black hole is often described by what cannot escape it. Yet some of the most spectacular black hole events are visible because of what happens before matter crosses the point of no return. When a star passes too close to a massive black hole, tidal forces can overwhelm the star's own gravity. The side of the star facing the black hole feels a stronger pull than the far side. The difference stretches the star, distorts it, and eventually tears it apart. Astronomers call this a tidal disruption event. The phrase sounds clinical. The reality is a star being pulled into luminous ruin. The shredded material does not simply fall inward all at once. Some of it may be flung away, while some forms a hot, bright stream or disk around the black hole. As gas collides, compresses, and heats, it emits intense radiation across ultraviolet, optical, and X-ray wavelengths. From far away, the event can momentarily outshine the host galaxy's central regions, appearing as a sudden flare where little had changed before. The star's death becomes visible precisely because the black hole feeds messily. Gravity destroys the star, and friction, heat, and orbital chaos turn that destruction into light. Tidal disruption events are especially valuable because many supermassive black holes spend long periods in relative quiet. At the centers of galaxies, they may sit with little nearby material to consume, nearly invisible except through the motion of surrounding stars. Then, a passing star wanders too close, and the black hole announces itself. For months or years, astronomers can watch the flare rise and fade, using it to estimate the mass of the black hole, the behavior of the debris, and the physics of accretion under extreme conditions. A single doomed star can illuminate a hidden gravitational engine. The violence here is intimate compared with a galaxy collision or a gamma-ray burst. It is the destruction of one star by one black hole, a close encounter governed by distance, mass, and trajectory. Yet the scale remains enormous. A star larger than the Sun can be stretched into a stream, wrapped around a dark center, heated until it glows with energies far beyond ordinary starlight. The black hole itself may remain unseen, defined by the luminous evidence of what it has taken. In that sense, a tidal disruption event is astronomy by aftermath. We infer the devourer from the wound. There is a deep unease in this kind of cosmic violence because it gives gravity a predatory shape. Nothing hunts in any conscious sense, yet the geometry of space-time can still create a trap. A star moves along its path, perhaps for billions of years, until a small change in orbit brings it within the tidal radius of a massive black hole. Then the mathematics of gravity becomes physical destruction. The star's surface, core, and atmosphere lose their identity as a single body. What remains is a flare, a stream, and eventually a contribution to the black hole's mass. Some black holes do not feed quietly. In the early universe, and in some active galaxies today, supermassive black holes consume enormous amounts of gas. The material forms an accretion disk, spiraling inward, heating through friction and compression until it shines with immense power. These systems can become quasars, among the most luminous, persistent objects in the cosmos. A quasar can outshine the combined light of all the stars in its host galaxy, even though the engine driving it may occupy a region smaller than the solar system. The brightness comes from matter losing gravitational energy as it falls toward the black hole. In some active galactic nuclei, powerful jets are launched from near the black hole, traveling outward at speeds close to light. The exact mechanism is still an area of research, but magnetic fields, rotation, and accretion play central roles. These jets can extend across thousands or even millions of light years, piercing intergalactic space and inflating enormous lobes of energetic particles. When one of these jets points nearly toward Earth, the object is called a blazar, and its brightness can vary dramatically as relativistic effects amplify the emission. A galaxy's central black hole becomes a cosmic lighthouse with a beam made of plasma and radiation. The violence of jets is not limited to the region near the black hole. As the jet travels, it slams into surrounding gas, drives shocks, accelerates particles, and reshapes the environment of the host galaxy. It can heat gas that might otherwise cool into new stars, influencing the evolution of the galaxy itself. This means black holes do more than consume. Through feedback, they can regulate star formation, sculpt galactic atmospheres, and alter the fate of vast systems. Their violence becomes architectural, changing the large-scale structure of the place that contains them. Quasars also let us look backward in time. Because many are billions of light years away, their light began traveling when the universe was young. Observing them means studying ancient black hole growth, early galaxy formation, and the conditions of a cosmos still assembling itself. Their violence is therefore historical. It belongs to an era when galaxies were richer in gas, collisions were more common, and black holes could grow rapidly. In the glare of a quasar, astronomers see a young universe where gravity had already learned to build engines of extraordinary power. There is something almost impossible about the scale. A black hole defined by darkness at its horizon can produce some of the brightest phenomena ever observed because of the matter surrounding it. The object itself remains hidden while the environment becomes incandescent. Jets carry energy far beyond the central region, turning a compact engine into a structure larger than many galaxies. Among the violent events in space, quasars and jets show a slower form of catastrophe, sustained, organized, luminous, and capable of changing the destiny of entire galactic systems. Cosmic violence does not belong only to exotic objects. Ordinary stars can erupt with enormous force, and the Sun, calm as it seems from Earth, is a magnetic star capable of producing flares, coronal mass ejections, radiation storms, and geomagnetic disturbances. Solar flares occur when magnetic energy stored in the solar atmosphere is suddenly released. Particles accelerate, plasma heats, and radiation erupts across the electromagnetic spectrum. Coronal mass ejections can throw billions of tons of solar material into space. If directed toward Earth, they can disturb satellites, power grids, communications, and the planet's magnetic environment. The Sun is mild compared with many red dwarfs. These small, long-lived stars can produce powerful flares relative to their normal brightness. A planet orbiting close enough to receive Earth-like warmth around a red dwarf may also sit near the region where stellar activity can be severe. Repeated flares and particle events may erode atmospheres, alter surface chemistry, and challenge the survival of life near the star. This matters because red dwarfs are the most common stars in the galaxy, and many known rocky exoplanets orbit them. The search for habitable worlds must therefore reckon with stellar temperament. A flare is a local event on the surface or atmosphere of a star, yet its consequences can reach planetary scales. On Earth, the magnetic field and atmosphere provide protection, but modern civilization adds vulnerability through electronics, satellites, navigation systems, and long power lines. The Carrington event of 1859, the most famous historical geomagnetic storm, produced spectacular auroras and disrupted telegraph systems. A similar event today could be far more costly because the technological layer around the planet has become part of our nervous system. Space weather turns stellar activity into a practical concern. This form of violence is subtle because it comes from a familiar source. The Sun gives Earth daylight, climate, seasons, and energy. It also throws charged particles and magnetic disturbances into the solar system. The same star that makes life possible can threaten the instruments life has built. That dual role belongs to many astrophysical objects. A star can be a source of warmth and a source of radiation hazard. A planetary system can be habitable in one era and hostile in another. Stability in space is often conditional, maintained by fields, distances, atmospheres, and timing. Stellar flares remind us that violence in the universe exists across every scale. A gamma-ray burst may be rare and distant, a supernova may happen once in a star's life, but magnetic activity can be routine. For planets close to active stars, danger may arrive in repetition rather than spectacle. Habitability depends not only on being in the right orbit, but on enduring the moods of the star. The most violent events in space are sometimes brief cosmic disasters. Other times, they are the weather of a star made harsh enough to shape the fate of worlds. Before stars die or black holes feed, there is another kind of violence, older and closer to home: impact. Planetary systems form from disks of gas and dust where small grains become pebbles. Pebbles become rocks. Rocks become planetesimals. And planetesimals collide until planets emerge. This process is not gentle assembly. It is construction through collision. Early planetary systems are crowded with debris, unstable orbits, and bodies large enough to shatter landscapes. The Moon itself is widely thought to have formed after a giant impact between the young Earth and a Mars-sized body, an event so large that it melted vast amounts of material and threw debris into orbit. Impacts continue long after planets form. Asteroids and comets preserve leftovers from the early solar system, and occasionally their paths cross planets. On Earth, impact craters record a history of sudden violence from above. The Chicxulub impact around 66 million years ago is linked to the mass extinction that ended the reign of non-avian dinosaurs. The asteroid did not need to be planetary in size. Its speed supplied the energy. When it struck, it excavated rock, triggered fires and tsunamis, blasted material into the atmosphere, and helped drive global environmental change. Cosmic violence entered biology through a single collision. On other worlds, the evidence is even clearer. Mercury and the Moon are scarred by craters. Mars carries enormous impact basins and volcanic provinces shaped by ancient trauma. The outer solar system contains moons whose surfaces show fractures, basins, and resurfacing events that speak of bombardment and internal stress. Jupiter, with its immense gravity, has been struck by comet fragments, most famously during the impact of Comet Shoemaker-Levy 9 in 1994. The event gave humanity a direct view of large bodies colliding with a giant planet, leaving dark scars in Jupiter's atmosphere visible through telescopes. Planetary impacts matter because they combine chance with inevitability. In any system with many moving bodies, collisions will happen. Gravity rearranges orbits, resonances shift paths. Encounters with planets can fling small bodies inward or outward. Most impacts are minor, but rare large ones can alter climate, oceans, atmospheres, and life. A planet's history is therefore partly written by what has struck it. Every crater is a preserved moment of transferred energy, a place where motion became heat, pressure, excavation, and sometimes extinction. Impact violence is also one of the few cosmic hazards humanity can realistically study with practical defense in mind. Surveys search for near-Earth objects. Missions can test whether a spacecraft can alter an asteroid's trajectory. Compared with gamma-ray bursts or supernovae, asteroid impacts belong to a scale where warning and intervention may be possible. That makes them unusual among cosmic catastrophes. They are ancient, destructive, and frightening, yet they also invite planning. In a universe of overwhelming forces, this is one kind of violence that intelligence may learn to anticipate. When galaxies collide, the event rarely resembles a collision between solid objects. Stars are so far apart that direct stellar impacts are uncommon, yet the gravitational violence is immense. Two galaxies passing through each other can stretch into tidal tails, distort spiral arms, trigger waves of star formation, and drive gas toward their centers. The collision unfolds over hundreds of millions of years, too slowly for human senses, but on the scale of galaxies it is a profound upheaval. Entire stellar populations are rearranged. Gas clouds compress. Black holes may begin feeding. New stars ignite in regions disturbed by the encounter. The Milky Way itself is on a future path toward merger with the Andromeda Galaxy. This will happen billions of years from now, long after the present age of Earth has passed into a different solar future. When the galaxies meet, the night sky, if any observers remain on a surviving world, would change beyond recognition. Andromeda would grow larger across the sky, then the two galaxies would pass, distort, separate, and return until they eventually settle into a new merged system. The Sun may avoid direct collision with another star, yet its orbit through the galaxy could be transformed. Galaxy collisions are violent through accumulation. No single instant contains the entire catastrophe. Instead, gravity works across vast distances, pulling streams of stars into arcs, stirring gas, and changing the rhythm of star formation. In some mergers, gas driven into the central regions can feed supermassive black holes, producing active galactic nuclei or even quasar-like phases. The collision of galaxies can therefore awaken other forms of violence. A slow gravitational dance becomes fuel for fast radiation, jets, and the birth of massive stars that may later die as supernovae. This slow violence is also creative. Many galaxies in the universe bear the marks of past mergers. Elliptical galaxies, stellar halos, streams, and disturbed structures all record gravitational encounters. The Milky Way has absorbed smaller galaxies before and continues to interact with satellite systems today. Galactic identity is therefore not fixed. A galaxy is a history of accretion, collision, stripping, and renewal. The stars we see as belonging to one grand structure may have been born in different systems, captured through ancient encounters. There is a grandeur in galaxy collisions precisely because they stretch the meaning of an event. A human disaster is measured in seconds, days, or years. A galactic merger can last longer than complex life has existed on Earth. Yet it remains one event, one gravitational transformation from first approach to final coalescence. It teaches us that cosmic violence does not always roar. Sometimes it unfolds as a slow rewriting of space, too vast to see in motion, clear only when telescopes compare one galaxy with another and reconstruct the drama frozen in their shapes. Any discussion of cosmic violence eventually approaches the early universe, although the word explosion can mislead. The Big Bang was not a bomb detonating inside empty space. It was the rapid expansion of space itself from an extremely hot, dense early state. In the first moments, the universe was a sea of particles, radiation, and fields, far beyond ordinary conditions. Matter as we know it had not yet settled into atoms. Stars, galaxies, planets, and black holes did not exist. There was no sky, no center, no outside region into which the universe expanded. There was only the universe becoming larger, cooling as it grew. The early universe was violent because everything was energetic, dense, and rapidly changing. Fundamental forces separated. Particles formed and annihilated. Protons and neutrons emerged. Light could not travel freely for hundreds of thousands of years because the universe was filled with charged particles that scattered photons. Only after atoms formed did the universe become transparent, releasing the radiation we now observe as the cosmic microwave background. That ancient light is not violent in appearance today. It is cold, faint, and smooth. Yet it is the cooled remnant of an era when the entire observable universe was filled with fire. From small fluctuations in that early density field, gravity began its long work. Slightly denser regions attracted more matter. Gas gathered. The first stars formed, likely massive and short-lived, enriching the young cosmos through their deaths. Galaxies assembled through collapse and merger. Black holes grew. The violent events described throughout this script are descendants of that first hot beginning. Supernovae, gamma-ray bursts, neutron star mergers, quasars, flares, and impacts all occur inside a universe whose original conditions allowed matter to clump, ignite, collapse, and collide. The Big Bang belongs in a different category from later cosmic events. It was not an explosion within the universe. It was the opening condition from which the universe's later violence became possible. Every star that dies, every galaxy that merges, every black hole that feeds, every planet that forms through impact, is part of an unfolding history that began in a state of extraordinary density and heat. The violence of space is therefore not an interruption of cosmic order. It is one of the ways order appears. This is the deepest perspective the subject offers. The universe does not build by preserving calm. It builds through transformation. Matter collapses into stars. Stars forge elements. Elements scatter through explosions. Gravity gathers debris into planets, and life emerges on at least one world capable of looking back. The most violent events in space are terrifying because they reveal powers far beyond human control. They are also the reason there is anything complex enough to fear them. We live downstream from catastrophe, made from the remains of ancient fires, sheltered for a moment inside a quiet atmosphere beneath a violent sky. The most violent events in space do more than destroy. They expose the hidden machinery of the universe. Supernovae reveal the life cycles of stars and the origin of elements. Gamma-ray bursts show how black holes can be born in beams of high-energy light. Neutron star mergers allow scientists to detect gravitational waves and trace the creation of heavy metals. Magnetar flares demonstrate the power stored in magnetic fields under extreme density. Tidal disruption events uncover black holes that would otherwise remain silent. Solar storms connect the behavior of a star to the fragility of technology around a planet. Each event also expands the range of what physics must explain. In laboratories on Earth, we can test matter, light, magnetism, nuclear reactions, and gravity within limits. The universe exceeds those limits naturally. It creates densities we cannot reproduce, magnetic fields beyond engineering, velocities near light speed, and gravitational fields that reshape space-time. Violent events are therefore not only spectacles. They are experiments conducted by nature, observed from a distance, interpreted through mathematics, instruments, and patience. Every detection is a fragment of an impossible laboratory. There is another reason these events matter. They place Earth in context. Our planet feels large from the ground, and human history can seem vast when measured by memory, monuments, and generations. Against cosmic violence, Earth is delicate. Its atmosphere is thin, its biosphere rare in our experience, its civilizations recent and technically vulnerable. This should not lead only to fear. It can also sharpen the value of the calm we inhabit. Stability is not the default condition everywhere. A habitable world is a temporary agreement between star, orbit, atmosphere, magnetism, chemistry, and time. The night sky appears peaceful because most of its violence is distant, delayed, filtered, or already over. Telescopes change that illusion. They reveal stars dying in remote galaxies, black holes tearing apart passing stars, jets cutting through intergalactic space, and bursts of gamma radiation arriving from events older than humanity by billions of years. The darkness above us is full of history in transit. Some of it is gentle starlight. Some of it is the last signal from matter under extreme stress. Astronomy is the act of learning to tell the difference. To look at the most violent events in space is to understand that the universe is not fragile in the way we are. It can absorb collisions of galaxies, the deaths of stars, the birth of black holes, and the tearing of matter into plasma. Yet within that enormous violence, fragile things can appear. Planets cool. Oceans gather. Chemistry learns repetition. Life begins, thinks, builds instruments, and detects the distant flash of disasters it could never survive up close. The cosmos is violent beyond measure, and still, for a brief interval, it has produced witnesses. There may be events more violent than anything we have yet observed. Some belong to theory, some to the early universe, and some may be rare enough that no human instrument has captured them directly. A star could pass near a black hole in a way that produces a jet aimed across cosmic distance. A pair of supermassive black holes could merge, sending gravitational waves through the fabric of space-time with power beyond ordinary comprehension. A massive star in the early universe could collapse in a way unlike the stellar deaths nearby. The universe is old, vast, and inventive in its extremes. The difficulty is that cosmic violence often hides behind distance and time. The most powerful events may occur in regions obscured by dust, in wavelengths human eyes cannot see, or at distances where signals arrive faint and stretched by expansion. Astronomers build instruments for that reason: gamma-ray satellites, X-ray observatories, radio arrays, gravitational wave detectors, neutrino experiments, optical surveys, and infrared telescopes capable of seeing through dust and into earlier cosmic eras. Each new instrument opens another window, and each window reveals that the universe had more ways to be violent than we previously knew. Yet scale alone is not the only measure. A supernova can destroy a star. A gamma-ray burst can release astonishing energy in seconds. A magnetar flare can shake a dead star's magnetic field. A tidal disruption event can turn a star into a stream around a black hole. A solar storm can threaten a technological civilization without harming the planet itself in the same way. Violence depends on distance, target, duration, and consequence. The universe contains explosions that would sterilize nearby worlds and slower events that reshape galaxies over epochs. Destruction has many tempos. This is why the subject resists a simple ranking. The most violent event is different depending on whether we ask about total energy, brightness, speed, density, gravitational power, magnetic intensity, or biological consequence. A galaxy merger may involve more mass than a supernova, but its violence is spread across hundreds of millions of years. A gamma-ray burst may last seconds, yet it can be the brightest event in the observable sky. A magnetar flare may come from a small object, yet its magnetic force belongs to the edge of physics. The universe does not offer one form of extremity. It offers a whole hierarchy of extremes. The final lesson is therefore larger than any single catastrophe. Space is not empty calm surrounding isolated stars. It is a dynamic arena where gravity builds structures, fusion lights them, magnetism twists them, radiation reveals them, and collapse transforms them. The most violent events in space are not rare exceptions to an otherwise motionless cosmos. They are part of the engine by which the universe changes. Through them, matter is rearranged, elements are made, black holes grow, galaxies evolve, and distant observers learn what reality can endure. Every violent event leaves an afterlife. A supernova leaves a remnant, a neutron star, or a black hole. A neutron-star merger leaves gravitational waves, heavy elements, and perhaps a new compact object. A tidal disruption event leaves a black hole slightly more massive and a galaxy briefly marked by flare light. A solar storm leaves disturbed magnetic fields and data in human instruments. A galaxy collision leaves a new structure that future astronomers might mistake for something eternal unless they learn how to read the scars. In space, aftermath is memory made visible. This is the quiet return after the violence. The burst fades, the shockwave expands, the jet weakens, the glowing debris cools. Telescopes continue watching as light curves decline and spectra change. What remains may look serene again, especially from far away. But serenity in astronomy often means that the loudest part has passed beyond our ability to hear it. The universe keeps the record in motion, composition, radiation, and shape. A nebula can be a grave. A stream of stars can be a fossil. A black hole's flare can be the last readable trace of a vanished sun. For a viewer on Earth, these events offer a strange emotional mixture. They are horrifying, beautiful, remote, and foundational. They describe powers that could erase worlds, yet they also explain how worlds acquire the elements needed for mountains, oceans, atmospheres, and life. The universe is not gentle, but gentleness was never required for meaning to arise. What was required was time, structure, chemistry, and the repeated transformation of matter through events of overwhelming force. We are made of material that has passed through violence and settled briefly into consciousness. So when we look at the night sky, we are looking at a surface of calm stretched over an abyss of activity. Somewhere, a star is collapsing. Somewhere, two dead cores are spiraling toward merger. Somewhere, a black hole is tearing a star into a luminous stream. Somewhere, a red dwarf is flaring over a close-orbiting world. Somewhere, a galaxy is being pulled into another galaxy's gravity, its shape slowly rewritten across ages. Most of it will never touch us. Some of it may never even be seen. Yet the light that does arrive carries a message as old as matter itself. The message is simple enough to feel and difficult enough to spend a life studying. The universe changes through force. It creates through pressure, reveals itself through radiation, and preserves its history in scars. The most violent events in space are not only scenes of destruction, they are chapters in the biography of everything. Long before Earth had oceans, long before life had eyes, long before there was anyone to name the stars, the cosmos was already exploding, merging, collapsing, and burning its way toward the possibility of witnesses. We are among those witnesses, standing in the afterglow,